From the Cambrian to the Silurian, there are an extraordinary group of worms called Palaeoscolecids. Not only are they turning out to be critical to understanding the entire evolutionary history of ecdysozoan, so everything that molts, like arthropods, but they also hold extraordinarily beautiful secrets that only an electron microscope can reveal. Well, and me. I can reveal them too. In fact, I'm just about to. Hello and welcome back. For anyone who's new here, my name's Joe and I'm a walking stereotype of a mad scientist. It's just the way it is, sorry. I'm a paleontologist and what I cover on here is a whole range of stuff about particularly the early part of the fossil record, Cambrian, Ordovician, Ediacaran, that sort of time, and hopefully will include quite a lot of things that you don't know about. Much anyway. Okay, so today we're going to be talking about possibly some of the most extraordinary fossils that ever turn up. They're just ridiculously gorgeous things when you see them up close, and you'd never guess from the first appearance of them. I happen to have here probably the largest, or one of the largest, specimens ever found. This is about 6-7 millimeters wide, which is on a par with the biggest ever described. This one we're writing up at the moment. It's only a small piece of it, just this sort of coiled tail part. Would have been much longer, but it's, yeah, quite impressive really. You see that, you can't miss it. Which you can't really say for this one, because I also happen to have probably one of the smallest ever found. Where is it again? Oh yeah, there it is. So it's on this piece of rock there. You can't see anything there. Let me stick it under the microscope and you might get a vague idea what I'm talking about. There you go. Isn't that exciting? Right, let's sort of go in a little bit closer on this one. I'll put a scale bar on at the moment. It's about 0.2 millimeters wide, I believe, so it's fairly small. And yeah, it's difficult to see much of anything there, isn't it? So I'm going to zoom in as far as we can possibly go on here and put in the polarizer and then do something with the brightness. Ah, there you go. Yeah, you can now see that there are a series of dots running across the centre of it. Little lines of dots. There you go, that makes it a Palaeoscolecid. Aren't you impressed? Admittedly, spotting that one isn't particularly easy, and it is inevitably from Castlebank, where every specimen that we've looked at, no matter how small, in an electron microscope reveals the most extraordinary fine detail that you could possibly want. And it's going to keep us busy because so far this is our box of Palaeoscolecids from Castlebank. And that box is 3 layers deep. And we think there's about 20-25 species, just based on what we can see under the light microscope. Yeah, it's going to keep us busy, as I say. But first we need to get on to why Palaeoscolecids are important, where they fit in the history of life, and what they can potentially tell us. So, the evolutionary tree of animals is divided into several major groupings. At the base, you have the non-bilaterians. These are things like sponges, cnidarians like jellyfish and so on, comb jellies, ctenophores, which don't have bilateral symmetry. They're normally some form of radial, maybe tetraradial or all sorts of variations, but they don't have a mirror plane going down the middle. And they also don't have a gut that goes all the way through the body. So those are a distinct group at the bottom. The rest of them are all bilaterians. They have some approximation to a bilateral mirror plane going down the middle and a through gut, so the mouth is only one end of it. Within the bilaterians there are 3 major groups: the deuterostomes, the spiralians and the ecdysozoans. This is where the names get a bit unfamiliar to quite a lot of you, I'd guess, but fear not, it all makes sense. So the deuterostomes should be the most familiar because you are one, I assume. Not quite sure. No, yeah. I'm not quite sure about you at the back there, but yeah, the rest of you certainly. Deuterostomes are the vertebrates, the phylum Chordata, and a few other groups, the echinoderms like starfish, and the hemichordates, which are the group that includes the graptolites. It's quite a small grouping though, there's only these 3 or 4 major phyla. The rest of them are separated from the deuterostomes on basic embryology, so which end forms first and stuff like that, so a very deep division in evolutionary history. But the rest of them are known as protostomes, and they're divided into the spiralians and ecdysozoans. So the spiralians are a very mixed group of lots of wormy, sluggy and tentacly things. So mollusks fit in here, brachiopods and bryozoans, annelid worms, flatworms. It's a whole array of things which share some embryological features and morphological features in common. The ecdysozoans are the ones that are left, and these at least have one nice, neat characteristic that separates them from the rest, which is ecdysis. They molt. If they want to grow, they have to shed their tough outer cuticle and then expand and grow a new one. And this is a feature of the arthropods, most characteristically, they're the familiar ones, but also things like nematode worms and various other groups. I'll give you a brief rundown of those groups so you know what we're talking about, because that will all become relevant when we start talking about these little Palaeoscolecids. So the arthropods are the most familiar ones. These includes everything with the jointed legs, apart from us. So things like spiders and scorpions, insects, crustaceans, and their softer, distant cousins, which evolved before the really tough outer cuticle. Things like tardigrades, the water bears, and velvet worms, onychophthans. These things which have these sort of stubby, loby legs rather than actually jointed ones. They all counted as panarthropoda, so the wider group of arthropods, if you like. Then we have the nematodes. These are hopefully not too familiar to you, although they're absolutely ubiquitous. And it has been said that if you removed the entire world and left just the nematodes behind, you'd still be able to see pretty much everything, including the beer mats on the German tables. They are extremely small. Most of them are very microscopic. They live in soil, they live in any damp habitats, and you'll find them anywhere you look closely enough. Many of them, though, are also parasitic. So the longest known nematode is, I believe, a parasite of sperm whales, which gets to about 9 meters, which isn't bad going for something that is very otherwise small and wormy. But their sister group, their very close relatives, are the horsehair worms, or nematomorphs, and these you don't tend to see very much. Again, mercifully, because they are also entirely parasitic in their juvenile stages. But occasionally you see these weird thread-like animals, almost like a long horsehair tangled up, in their adult phase when they become free-living. So it's a slightly odd life cycle, but you do find them occasionally in ponds, rivers, even in the sea. And they're an interesting group. Next up we have the priapulids. These are a fairly obscure group today, well known to zoologists, but not to many other people. And they've got this evertable proboscis with spines on that it can sort of stick out, catch things on and pull it back in, along with whatever was stuck to it. So the larger ones are quite active predators. Many of them today are very small, living not quite between sand grains, but down to a few millimeters body size. And then there's a few which are a bit larger. But if you go back to the Cambrian, there are many things that have been described as priapulids, and they were quite large. 10, 15 centimetres is fairly common for some of these really chunky priapulid-like things in the Cambrian. So they're an important group in the fossil record. Not much beside the Cambrian, but they're in the Burgess Shale type faunas, pretty much all of them, to be honest. So they're well worth knowing about. Aside from them, there are 2 other phyla, which are very obscure. Most people have never come across them because they are extremely microscopic. They're mostly myofaunal, living between sand grains and in marine mud, and they're known as the chinorhynchs and loricifrons. The Kynovinks have a common name of mud dragons, which is rather cute. They are lovely little things, sort of plated bodies with spines coming off them. And the Loricifilans are known as Loricifilans. I don't think anyone's ever bothered coming up with a common name for these, but they are incredibly ornate, gorgeous animals with bits sticking off everywhere. And they both have a sort of proboscis of sorts, but it's not retractable. So you can kind of see it's the same basic body plan as priapulids, but it's very highly modified. And presumably, because these are so tiny, it's been modified in the lineages leading to these as well. These, of course, are the living phyla as we see them today, but what did their ancestors look like? If we were to trace these lineages back, what did this main branch leading to all these phyla actually consist of? What were these things like? Well, that rather depends on the topology of the tree, the sequence of branches, and even that isn't entirely clear. So most groups seem to recover a monophyletic, that is a single group consisting of Kynovinks, Loricifilans and priapulids. However, that's not universally used, and there seems to be a bit of a conflict as well between the datasets that just use modern genetic data and those that include fossils and look at morphology. And when you do that, then it seems that some of the results, at least, are pointing towards some of these early priapulid-like animals actually turning up further up the tree, and you end up with priapulids being closer to arthropods than Kynovinks and Loricifilans are. So we really need to have a good look at these fossils and see what they can tell us, see if we can actually get to grips with where they fit. But what sort of fossils are we looking for? What do we actually know about what these animals along the backbone leading up the evolution of the ecdysozoa must have been like? Well, we know there were worms. We know that they had a tough cuticle, which they molted, because that's shared by all of them. We also know that they had a sort of circular mouth at the end, and in several cases, but not all of them, they had a proboscis of some form, whether retractable or not. And it's quite likely that at least some of the deeper parts of this tree had this retractable proboscis, or possibly retractable, possibly not. But beyond that, it's actually quite hard to guess. So to get much further, we are going to need some fossils. And this brings us to Palaeoscolecs, described in 1953 by Whittard from the Lower Ordovician Shanton Shales of Shropshire. This is quite a well-known deposit. It's very rich in trilobites. There's been a few other odd things have turned up there as well, but it's not regarded as a conservat lagostata particularly. So, the fossils are quite nice, but you don't expect to see a tangled, wriggly, worm-like thing sitting on the bedding plane. And when he found this, he described it as Palaeoscolecs, which translates as ancient worm. So, yeah, it's another of these cases where imagination of paleontologists strikes again. But it was a sensible name because they had no idea at the time what sort of worm this was. Various ideas were discussed, and it was assumed to be some sort of annelid, because it's very long, cylindrical, even thickness all the way along, and it's banded, it's annulated or segmented, so you see these very fine divisions all the way along, with a trace of quite ornate sort of cuticle on the surface. But this was left in uncertain interpretation for a good long while. Around the same sort of time, though, there were some odd little fossils turning up in micropaleontological samples, tiny little buttons with lumps on, which were called Hadmopanella. And these were of totally unknown origin. They were just little tiny phosphatic buttons which were coming out of dissolved limestones and Cambrian and Ordovician rocks. And they also were a bit of an enigma. It was only when 1989 was the first paper by Peter Kraft and Michael Mergel in the Czech Republic who started to find articulated and well-preserved sclerotomes, as we call them. So these little buttons all joined together, and it turns out that it was a worm-like form. a very elongate, cylindrical, banded worm with lots of very fine annulations. And suddenly this starts to tie things together. And then the papers started coming thick and fast. Muller and Hinz-Schallreuter in 1993 described a huge array of phosphatic cuticle fragments dissolved out of Cambrian limestones in Australia. And these started revealing the most incredible details of these bits of cuticle which were studded with tiny little plates. These plates are often 30, 40 microns wide, so they're pretty tiny things. But the detail that's preservable by this type of phosphatization was remarkable. And they're just incredibly gorgeous fossils. I mean, you see something like this in an electron microscope, you have no idea that it's going to be there until you put it in. And this led to a whole array of other papers when people started tweaking that these hadamopinellids, these little plates, were actually the buttons on the cuticle of Palaeoscolecids. In fact, Simon Conway Morris went back to the type specimens of Palaeoscolex and took latex casts very, very carefully and put the latex casts into electron microscopes and revealed this vast world of fine detail that even with Wittard's really good microscopy, you couldn't see that level of detail. And this again ties these things together. So there is now an array of Palaeoscolecids with diverse forms of plate arrangements and microstructures being revealed by very careful work around this time. There's one problem with this fossil record though. On the one hand, we have this gorgeous preservation of exquisitely fine detail in phosphatized fragments of sclerotome. We don't see the whole worm. We don't see the soft tissue. We just see bits of the cuticle. And on the other side, we get things like the original Palaeoscolex piscatorum, which has actually quite nice preservation of the cuticle in that case. But sadly, very little soft tissue. There is actually a gut trace, so there's some soft tissue going on, but we don't see anything like the proboscis in this material, which is a shame. And when we did start to see the proboscis being preserved, and it turns out it was genuinely there, what we're lacking is the fine detail. So in the Xinjiang biota, the first ones turned up which really look convincingly like Palaeoscolex with a soft body. And you have a very priapulid-like proboscis sticking out the end. But the preservation in Xinjiang of these skeletal, very fine details just isn't there. You can get a certain amount of detail of the plate morphology, but all of the tiny microplates and platelets which actually create the rest of the cuticle is just gone. The preservation is slightly limited in that it has been weathered, it has been slightly cooked, and you just don't get the same level of detail as we get in these phosphatic bits. And so far, we haven't yet got a deposit which actually preserves both with perfect detail of preservation. We're very hopeful on Castlebank. We do have one or two specimens where we do see the proboscis as well as exquisite detail of the cuticle structure, but it probably doesn't matter that much because there's enough information from both sets of different types of preservation to be able to tie it all together and give us a pretty good picture of what these animals were like. And if nothing else, they were very diverse. Even within this local area, the Bill Thinlire where we live, we have a really wide range of morphologies which show different patterns of growth, which have different arrangements of plates around the annulae. Some have a solid cuticle, others have a reticulate cuticle, in which the plates are sort of embedded into the spaces. We have many of the normal ones, where you have plates with little tubercles on, and then we have one thing, the extraordinary Wernia, which is known only from one site, and those plates have little arrows pointing into the intercalation, the boundary between these little annulations. And each annulation tends to preserve 2 rows of plates, but that varies enormously. There are some which are just densely covered with little plates. There are some which seem to have a single line of plates. There are some which have a single line of plates on one side, and as you follow it across the worm, you get into 2 or 3. It's a huge array of different morphologies within these structures. And that is potentially quite important, because it means either this was one group of worms which has diversified to a huge extent within a small branch of the evolutionary tree, or we are potentially seeing quite a lot of the evolutionary tree having very similar patterns. And that diversification is showing us that, in fact, many of these were not necessarily closely related. They may potentially occupy quite a wide range of the evolutionary history within ecdysozoa. That's one possible interpretation you could lead to. So do any of these animals tie in with the other groups of ecdysozoans that we already know? Well, there are some interesting parallels. For one thing, we can divide the Palaeoscolecids so far into two major groups. Technically, I should say the Palaeoscolecidans, which is the wider grouping, and then you have the Palaeoscolecids, which is the family Palaeoscolecidae versus the family Cricocosmiidae. And the Cricocosmiids are known only from the Cambrian of China, Zhejiang and similar deposits. And these ones are quite interesting in that they have many fewer plates. They have many fewer plates in an annulus, and those plates are larger. And this is interesting because when you look at the lobopodians in the Cambrian, things like Microdictyon, for example, they have paired plates along their back, which are apparently phosphatic. So you have lobopodians, so very early ancestors or relatives of the arthropods, which have these structures that could be related to what we see in the Cricocosmiids. You can imagine there being, very easily actually, a continuum between the Cricocosmiids and these early lobopodians. We don't have obvious things filling the gaps directly, but you could imagine those things existing. The Palaeoscolecidae are much more diverse. They are the much larger group, and these are the ones that occur throughout the Cambrian, Ordovician, and even into the Silurian worldwide. And these are much more like the priapulids. There is a Burgess Shale priapulid called Louisella, which Conway Morris has compared directly with this sort of little cuticle ornamentation of tiny little plates, possibly? Little dots over the surface, which looks similar to the arrangement of plates in Palaeoscolecids. And it's possible that this is showing some sort of gradation between things which are very like the early priapulids, at least things we've called priapulids, and that may also be an evolutionary continuum. There are lots of problems, though, when you start to try to slot these in. For example, from everything we know from the genetics, the sister group of arthropods today is the nematodes and nematomorphs, and they don't show anything like the structures we see in Palaeoscolecidans. There's no proboscis, there's no plates. They must have simplified their body form significantly in order to get to where they are now. And that's fine. These things happen after all. When you look at the other end, you have the priapulids, which today, and the definite priapulids we see in the fossil record also, do not have any phosphatic plates. They don't bimineralize phosphate. So that means that either the lineage leading to modern priapulids lost the phosphate in the plates, or that the lineage leading to arthropods and nematodes gained these phosphatic plates after the split from priapulids, and those things that look like it, like Louisella, for example, probably are not priapulids. They're more towards the arthropod branch than they are towards modern priapulids. And that also is possible. The problem is that we just don't know quite how everything fits together yet. We have so few species of Palaeoscolecids which have the proboscis preserved, at least in fine detail. And when we do have the proboscis, we don't see the very fine cuticular detail. And this means that it's very difficult to come up with a coherent evolutionary scenario for even the Palaeoscolecidans themselves. So looking at the internal evolution relationships, we don't know quite how things evolved into which other groups. And this is challenging. It means we haven't got any polarization for the characters. We don't know which ones evolved first, which ones came later, which might be ancestral. There's a lot of guesswork involved at the moment if you were to try to put this into any sort of real phylogenetic evolutionary scheme. At the moment, most of the work trying to look at the phylogenetic placement of Palaeoscolecidans is based on choosing half a dozen Palaeoscolecids and then slotting them in with lots of other groups of arthropods, ecdysozoans, modern lineages, and so on, and seeing where they fit. And the answer that you get depends on your analytical approaches. There's been a bit of discussion of this in the literature in recent years, and it depends to some extent on how you deal with coding inapplicable characters. So this might be a little bit abstruse for those who don't really know much about cladistics, but you have a data matrix of lots and lots of characters, and some characters will be dependent on other characters. So if you're talking about the ornament on the plate, that presupposes you have a plate. And it's how you deal with these sort of conflicts that can lead to a very different arrangement of which groups turn up where. That said, the information that we have, or at least the outcomes of these analyses that we have, seem to be showing that some of the Palaeoscolecidans, the Cricocosmiid, appear to be sister group to arthropods. So they're actually getting towards the base of this sort of early arthropod evolution. But I think analytically it's not yet certain. And the others are slightly deeper in the tree. There's a lot of unresolved bits where we don't know quite which one came off first, and you just got a string of species which all come off together. But they all seem to be turning up around the priapulids and higher, and above the Chinorhynchs and the Lorocyphelans, which kind of fits. It's all a general mishmash in there, with these worms fitting in some gaps, but we have as yet no stability at all as to exactly where. Are there any other worms that could help? Well, we do have some very interesting early fossils. Things like Ecdysozoan, which was originally described from the early Cambrian of China, exquisitely preserved, as being a stem group Chinorhynch. And it has this sort of slightly odd structure. It's kind of annulated, and it has these large plates with spines coming off them. And it's a really, really interesting worm. And something like that, with its little proboscis type thing, could indeed be showing us something that's getting towards a Chinorhynch. However, some recent analyses are suggesting that it turns up in a different place, maybe closer to the Palaeoscolecids, and there is certainly uncertainty among Chinorhynch specialists as to whether these things really are. They don't show quite enough features to be certain that it's on the way to being a Chinorhynch, even though it's very tempting to look at it in that way. It's also possible that this is not so much a Chinorhynch ancestor directly, as somewhere near the base of the tree of ecdysozoans, which is really, really interesting. If that does turn out to be true, then that's giving us a constraint for what the morphology of some of these earliest worms look like. And you can go from something like that relatively easily to becoming much more regularly annulated, reducing the plates to tiny ones and having lots of rings around it with many, many more plates, and you end up quite rapidly into Palaeoscolecid territory. What we need are a lot more worms, fossil worms, that don't obviously fit directly into the Palaeoscolecids, or the Palaeoscolecidans, but which are probably related to them. Ideally, we need these things with soft tissue. Ideally, we need things that look like they might be vaguely Ecdysozoan-like, for example. And what you want is sites with really extraordinary preservation of the cuticular detail and also preservation of the soft tissues. And if we had something like that, that would be really, really handy. And there would be something sort of very high on one's list to put in an electron microscope, for example. Yeah. Wouldn't that be nice? For the moment, though, all we can really say is that Palaeoscolecids are a wonderful group to work on. They're absolutely fabulous. There's so much more left to do with them. Just the sheer breathtaking beauty of these things when you zoom in and suddenly reveal this mass of plates and platelets and all the rest of it. It's just incredible stuff. And it's well, you'd think anyone would be really glad to work on these and find some more really interesting ones that actually tell us the answer, or whatever the answer is that we're looking for. But at the moment, I think it's becoming increasingly clear that they're not just a group on their own, that at least the morphology of these seems to resemble what you get in the main sort of backbone, if you like, of the ecdysozoans. That some of the branches coming off, like the priapulids and the chinorhynchs and so on, could all arise from something vaguely Palaeoscolecidan-like. And it may well be that there are some groups of these that diversify enormously, like the Palaeoscolecidae, and those form their own little clades. But amongst all this morass of tiny little things which have been poorly studied as yet, there are probably going to be things which are much closer to other phyla, much closer to telling us about how ecdysozoans really evolved into the forms that we know today. But what are the odds on being able to find some? Is it something that anyone can do? Well, yeah, I think it is, because on the one hand, you have the phosphatized microscopic remains that you have to dissolve out of limestone, which is a fairly specialist job, and you need the right sort of rocks anyway. On the other hand, you have the exceptional preservation, the Burgess shale type conservat lagerstätten, and not many people sadly get to work on those. But then what we're finding increasingly in mid-Wales is that there's a third type, that you also get compression fossils in shale, just fairly ordinary looking mudstones and siltstones, particularly siltstones actually. It tends to be slightly coarser rock than mudstone, relatively shallow water, sort of shelf type depth, where you get trilobites and graptolites and things like that there. And if you get articulated trilobites, for example, if you get complete trilobites, that's a really good sign. It means things are being buried fairly rapidly. You don't need soft tissue preservation to find at least partial Palaeoscolecids, because the cuticle itself is quite tough and it's biomineralized. When we're out in the field, we're always using one of these things, little 20 times hand lens, and with that you look at anything that looks like it might possibly be wormy. And we're talking about things usually less than 1 millimetre wide. So little black lines, often short segments of worm, 1 millimetre or so long, 0.3 millimetres wide. But if they look like they're a little bit wormy, then we take them back and stick them under a microscope. And with that technique, we've now got, I think it's 7 or 8 sites in the local area which have yielded Palaeoscolecids. Most of these we've already described, that was in a paper in 2012, but a lot of the rest are actually in Castlebank, so that's going to be ongoing work for quite a while. But we've also found them in the Avangam biota. They're quite small there, and they are obviously in the Llanfairpwllgwyngyllgogerychwr biota on a slightly larger scale. And you need a certain amount of at least unusually good preservation, but it doesn't need to be an established lagerstätte. And I think one thing I would recommend for everyone working in the Cambrian and Silurian is to really hone your search image in for these tiny little bits of maybe worms. Even if you're not getting completely soft-bodied animals, it doesn't matter. You can still get bits of Palaeoscolecid. And with a decent microscope, you can make out that they have got lines of plates going across. And at that point, you've just got to chuck them into an electron microscope and see what happens. And I know most people don't have one of those in their kitchen normally, but you know, there are ways and means. You can find someone who's working on the things and they'll be quite happy to help out, I'm sure. Right, that is an introduction to Palaeoscolecids. I suspect people might like to see more of them at some point, and certainly whenever we publish something we'll do a little video on those. But if you'd like to know more about, for example, the range of Palaeoscolecidan diversity in the bill-thin layer, that's something that I can very easily do. Let me know, and yeah, we'll see where it goes from there. But there's lots more to say about these things, I'm sure. Lucy's actually done quite a bit on Palaeoscolecids too, so I'll have to get her in for the next one. But thank you once again for joining me and staying to the end, and hope you've enjoyed it. You can't really go too far wrong with this group because they're just incredible things. And yeah, Good luck with finding some yourself. For those who don't know, there is also a membership option where we talk about more sort of secret ongoing work, and please do investigate that if you're interested, and we will see you again sometime. All right, see you soon. Farewell.